Students, welcome back to the second part of lecture number 40, and this is what is going to be your last part of your lecture. And as I put it on the slide, how do I sum it up? Summing up the whole course is a very difficult job. So, I was thinking about it, how to do it. As you know, summing up means how to put things together so that you understand everything. So, next 20 minutes or so we are going to do that, so that you can keep it as one last video, what are things we learn. So, first we started about definition of AI, how AI is important, and we don't need to explain it to anyone, right. Even the kids also know how AI is important, but they don't know that one thing, that AI has limited capabilities. That is something which you have to realize. AI has two parts, one is called machine learning and one is called deep learning. Machine learning deals with structured data, deep learning handles unstructured data like text, images, right. And machine learning, in which machine can automatically learn the patterns from the existing data. And we can actually do a lot of things using AI. We can do analytical problem solution, learning, observations, all kinds of things. And there are two types of AI. One is called narrow AI, which is that's what we are doing it. We can detect faces, plugging online contents, customer queries, online chatbots. But general AI is still a concept today. We are aiming to reach that. I don't think it is possible in a very small time frame. It is envisioned to be adaptable and reasonable as human being. Remember the words adaptable and reasonable. But why you want to use AI? Basic reason is to discover and design new materials. And what are the traditional way of designing new materials? First is trial and error, which we have been doing for ages, right. We try, do something, fail, learn from the failures, and then go back again, change the conditions. And this approach is a time consuming. Sometimes it will be like taking ages, not possible for a life of a human being to discover. And this is what is called Edisonian approach, because Edison and Tim have tested more than 3,000 designs of the bulbs between 1878 and 1880s. Within 2 years, they tested more than 3,000 designs of the bulbs. So, imagine how many people are involved and how many times they failed. To succeed, you need to fail. That is what is the real problem by Edison approach. But that is no longer possible. So, you have to think about something new. Then you have to understand how this subject or knowledge has changed from first paradigm to the fourth paradigm. First paradigm was empirical science, everything was empirical, that is below 1600, before the Galileo's time. And then comes second paradigm, which was basically model based science, correct. And finally, after 1950s, what we have basically something where we can correlate, understand the subject, correlate structure properties with performances. And this third paradigm came in 1950s, what is known as a computational science, which are basically simulation based. And there we can actually do a lot of simulation using computers, density functional theories, molecular dynamics, and this can provide us new ways to design materials. But that is not all. Then what you have is basically machine, AI based techniques, what is called a fourth paradigm. Okay, this is what is called a fourth paradigm, right. You can go back to my lectures, you can find out that. There we can handling data science. We have a lot of data, how to analyze the data, try to find out the trends. Just now we talked about in the last part or first part of this lecture. So, that is what is called big data science, and this is something which we are all living in, right. We can have predictive capabilities, clustering, relationship mining, anomaly detections, everything is built in this. Now, you understand the meaning of these sentences after all the lectures are delivered, you can understand that. So, this big data driven science is something which all of us going through, how to do that. So, this paradigm shift from first to second to third to fourth, especially the third to fourth, is very rapid. In last 50 years, between 1950 to 2000, the third paradigm has started. Now we have gone into fourth paradigm. So, this is something which you wanted to learn, that is what I started with. But we are doing materials. If you want to do materials modeling, you should know what is the basic thing of material science. Basic thing of material science is the correlation between processing, structure and property. And we spend quite a lot of lectures, almost like a 12 to 13 or 14 lectures on this aspect, try to understand you what are the basic aspects of material science, so that you can design new materials with target set of properties, discover new materials. And there we talked about fundamentals of structure, properties and all these stuffs, crystal structures, atomic structures, microstructures, nanostructures, atomic structures, okay. And we talked about different properties, mechanical, physical, magnetic, electronic, electrical, and we expected you to learn a full understanding of this correlation between structure and properties. That is not easy, remember that is the basic of material science. We have to integrate these basic things with the big data science, and that is my main motto when I design this course, so that you can get a lot of these basic concepts clear and apply this, or take the clue from this basic concept, apply this in the data science. And materials can be anything, but are they useful? That is what we talk about engineering materials. Engineering materials are ones which human extract or make for any utility. So, you can have different kinds of material like metallic materials, ceramics, polymers, composites. They are all called engineering materials because they are useful. Then in order to do that, you need to basically understand basic of material science, and also you need to also understand the correlation between the structure, property and processing, so that you can apply this in design of materials. And basic thing is the microstructure. That is what is controlling the material properties. And there is a key link between this synthesis or processing of materials and the properties. And structure means starting from atoms, crystal structures, grain structures, or finally microstructures. This is what is the structures. You have grains, boundaries, defects, everything is going to come into picture. You can have single phase microstructure, multiple microstructure. Like steels, you have alpha iron plus cementite. In pure iron, you have only grains of alpha iron, right. So, this is the difference between that. When you have 2 phase or 3 phase microstructures, distribution of the phases are also going to play an important role. Interface between the phases are also going to play an important role. Then you have defects. You cannot have perfect things in the world, right. Nanoparts are perfect. So, imperfections in crystal structures are very, very important. You can have point defects, you can have line defects like dislocations, you can have surface defects or 2D defects like twinning. All these defects play a very important role in materials. And we talked about a lot of engineering materials, metals, ceramics, polymers, you can see non-metals, composites, ceramic, plastics, many things. But metals are the largest group. You can have steels, you can have aluminum alloys, you can have titanium alloys. I try to avoid it because that is a massive thing. And then you can have ceramics. Ceramics are compounds the metal and non-metals. They often form oxides, carbides, nitrides. They have much different properties than the metal materials. They can have very high melting temperatures, very high compressive strength, but they are very brittle. They have low thermal electrical conductivities, right. Tungsten carbide and zirconium carbide, aluminum oxide, zirconium nitride, all these examples we are given. These are there. You can have hydroxyapatite, kaolinite, sialin. Then you have whole lot of things in polymers. You have thermoplastic, thermosets, elastomers. You can also have amorphous materials present like glasses. Many of the polymers are actually amorphous. So, the amorphous materials are widely present in the world and we cannot avoid it. Compared to the metallic and ceramics, amorphous materials are mostly either glass or polymers. So, amorphous materials have random structures, okay. Glass is a amorphous structure of sodium oxide, calcium oxide, silicon dioxide, right, remember that. And there is no grain boundaries, there is no order atomic elements in the glasses, that is what is going to happen. So, in a polymer you can have complete random chains of molecules, you can have crystalline plus amorphous structures also. But that was the different structures. You can also have different property like tensile, compressive, shear in mechanical properties. You can have electrical properties like conductors, insulators, semiconductors. We discuss different models of that, and you can have metals, ceramics, polymers, semiconductors again. Then you have magnets. Magnetic properties are very important, right. They actually provide you a lot of interesting insights of that. And then we went into what is known as the processing conditions operations, different kinds of processing operations, because those are the structure properties. Then you have to talk about processing conditions, shaping operations, how do you shape a component, how can you improve properties like there will be heat treatments or something. You can do surface treatment also, like clean, coat, treat, deposit materials. And shaping components are 4 types. We talked about it: certification processing, particular processing like a sinterings, deformation processing, and material removal processing like machining or something, right. So, in certification processing we have to pour a liquid metal into a cavity and solidify, you can see that. In powder processing we take a powder as a source of material, sinter them to form a component, and in deformation processing we take any bulk material, deform it plastically to give a shape. Machining is removal process. Machining means we cut something, remove materials to give a shape, right. So, these are the different shaping processes we discussed, and more important thing is the bulk deformation processing like rolling, forging, extrusions, stage forming, bending, sheet metal forming, all kinds of things possible. We discussed quite a bit of this. Powder metallurgy, we take the powders, we process, characterize the powders, then we do pressing and sintering, and we can actually do other kinds of techniques also. So, by pressing we create a grain compact, and this grain compacts are then basically sintered to obtain this sinter products. So, this was about the basics of material science, which I covered in last 5 minutes, okay, but it will take you one full course or maybe more than that. So, please look into different course structures at NPTEL or other fora where you can actually get a knowledge of that. Then comes the concept of machine learning, how it is different from your conventional approach like trial and error methods. And we can that we have trial and error based discovery of design materials. We can also have third paradigm where you can use simulations like quantum mechanics, molecular mechanics, all kinds of things, we can do that. But we can also do high throughput skinning, we can skin the materials and get a lot of understanding of that, right. And machine learning models actually methods can be utilized to speed the material development cycles, and machine learning is something which we can learn from data. I discussed a lot about it, how the task is important. There are 2 types of machine learning, supervised and unsupervised. Supervised means it develops predictive model based on the level data which has both input and output. Unsupervised means you do not have level data, you have only either input no output or output with no inputs, right. So, you can actually use classification regression based models for supervised learning and clustering for unsupervised learning. Okay. And this is the machine learning workflow. Let us not discuss about this. Supervised learning actually requires training, and they are by level data. Level data, I explain you how level data can be obtained from supervised learning. So, first model we talked about is simple regression. It is a statistical model that utilizes one quantitative independent variable x to predict quantitative independent variable y. You can have many quantitative independent variables also, and we can also do the analysis. Easy ways to do is a linear model. We can have a lot of nonlinear model possible. Linear models will have some random error also, you can see that, and these are actually linear combinations of these variables. We can do classifications. I talked about a lot about classification problems. Machine learning can do a classifications easily, and classification based on discrete values levels, even you can also do other kinds of levels also possible, and you can do numerical predictions also like credit null, medical diagnosis, fraud detections, all kinds of things. We talked about different kinds of classification problems like decision trees, support vector machines, and random forest, and also k-nearest neighbors, right. Decision tree is something which we started discussing about it. This example like whether can you play tennis depending on weather, right, signing your work as friend. Then we talked about SVM, support vector machine. How can you have a maximum margin? Remember I talked about roads, right. Maximum margin is a linear classifier, and here you can actually separate data with the maximum margin. How we can do that is what is called linear SVM does, and this is something which widely used in material science. You will be using that. Then we talked about quite a bit of artificial machine learning, because this is important for this. It basically uses the concept of how the brain works, how the brain has humongous networks, how it works that way. and it is basically based on dendrites, cell bodies, and synaptic and axons, and that is the typical elements of any action. We can actually have input variables, we can put weights, we can then add it up, and then we can get we can put a transfer functions, activation functions on these additions and get output. So, this transfer and activation functions can be different types, which you have discussed already in your lecture. You can see that how this can be done. You have inputs, and then you can weights, multiply the inputs to the weights, add it up, and put the activation function, get output. Right? That is what is called the ANN does. We can also have k nearest neighbors models. This is it is basically we can do a majority category levels, and very easily. Then we talked about clustering, which is nothing but unsupervised models, and you can have centroid models, connectivity models, tensoroid models. It is a task of dividing data into meaningful groups. That is what is called clustering, and it is aimed to forming groups of homogeneous data points from a heterogeneous data sets. So, centroid model is widely used, k-means algorithms. You can have hierarchical algorithms, other things also possible. Let us not talk about here quite a bit, because these things can be easily obtained, and you can also have density based, connectivity based, distribution based clustering also possible. Clustering is very important. Please do spend time on this, learning the clustering algorithms. Then after machine learning, we into deep learning. Deep learning is typically based on artificial neural networks, and that is what we spend a lot of time on how to do that. You can use computer visions, it can use NLPs to healthcare dynamics, diagnostics, and automatic diving also possible using deep learning models, but it requires a lot of data. Without that, you cannot do. You can have computer visions, you can have also NLP as well as reinforced learning. You can have use agent to learn for you. That is what is called reinforced learning. And there you have, when you have to talk a lot of data, you have to talk about different types of data like sequential data, 2D data, or tabular data, right? And each of these data are very important when you model. And for deep learning, you will use lot of data. Small data, machine learning is good, deep learning is not good. You need a certain amount of data to a good DL modeling. So, we talked about ANN, CNN, RNN, autoencoders, DBN, and many others. Advanced models also, that. And these models actually depends on feature engineering, hardware dependence, data types, and they sometimes are called black box type. They very difficult to interpret these models. So, this is the chart we talked about it. We talked about supervising models like MLP, multi-layer perception, CNN, RNN. We talked about unsupervised like GAN, AE autoencoders, SOM, RBM, DBN, and we also talked about hybrid models, mixture of these different kinds of models, right. We spend a lot of time in understanding deep learning models, and I do not want to discuss each of these. CNN is something which is widely used for image processing models. That is what we did. Then we talk little bit about advanced models like advanced DLs, which are widely used. One such model is NLP, natural language, and from there we went to material informatics, right. That is what we talked about in last 4 or 5 lecture. NLP is something which is going to come more in material informatics, how to generate data and do that. And NLP has different kinds of phases: lexical analysis, syntactic analysis, semantic, discourse integration, and pragmatic analysis. And this is a very powerful tool which will come back. And finally, we also talked about it, why you want to do that. You have materials design at different length scales. You can have the properties, performance structures, and processing, and these are connected to get an idea about performance, right. That is the key idea. So, when you talk about integration of data science with these things, what is called the length scale, first you start with the CalFERD, and CalFERD provides you calculation of phase diagrams that gives you all kinds of property like entropy, enthalpy, Gibbs energies, diffusion coefficients, heat capacities, and also it can provide you sometimes calculation provides you many other data. But microstructure model is very important. That is what you need to use phase P modeling, and phase P modeling use the interface. There is a diffuse interface model where you can actually add an interface term and do that. Then finally, one of my colleague from other IIT Kharagpur is talked about computational chemistry and material science like electronic structures, DFT calculations, as well as your molecular dynamic simulations. Like this is what is good. Newton laws of motions are used for molecular dynamic simulations. Finally, also we talked about it, some bit of data preprocessing and other quality data cleaning, data integration, reduction and transformations. And why you need that? We need accurate data which is complete, consistent, timely, believable, interpretable. That is why we need to do data processing. Please remember that data preprocessing is the critical step when you want to do a machine learning based models. I do not want to go into details of that. Finally, you have to do a model score, that is what F1 score does, how a model is performing good or bad or not, and this is nothing but a harmonic mean of the precision and the recall, and we talked about it, how what is it, and at the end I talked about it material informatics, which is based on information data science, and it is very important tool nowadays to discuss about it. And as I told you, we are going to develop a new course on material informatics, maybe after 1 year or so you will get to know about it. And this course will talk about details of the material informatics, because data science is going to be very important in material science also. And I will discuss all these aspects, I do not want to go back into that. I just like to say you that I hope you have enjoyed these different lectures of this course, and this has provided you some basic concepts of the machine learning and deep learning and informatics, on which you can build on. This is like a foundation, and now on the foundation you can grow your knowledge and gain more and more understanding of that. And I hope also my TS has given a lot of time to answer your questions, explain different kinds of knowledge, these concepts by giving examples, by giving some kind of a programs or so. We tried best to do that, and this requires, I understand this requires a lot of tutorial kinds of things, but it is not easy to do tutorials in an online based course. Sometimes very difficult. Normally we do tutorial when you teach the course in the offline mode. There we spend some time on tutorials, explain different examples, to bring different examples to explain different concepts, but it is not possible here so likely. But I must tell you, the participations of these kind of online descriptions were not very enthusiastic, and TAs have also informed me that out of 8,000 students, hardly about 1,000 students used to participate. That is another important aspect we have to work on, how to make it more applicable to you. And last thing I want to tell you that I enjoyed developing this course, because I learned a lot, and this is a very interesting concepts on which we will build on more and more courses. With this, let me give you a big thank and end this course by telling you that take care and do well. Thank you.